So let's look at what are we going to do today. We'll be looking at, we'll be introducing you to Hadoop. We'll look at the various components in the Hadoop ecosystem. We'll also look at the core components of Hadoop, which is HDFS and MapReduce. We'll go into details of HDFS architecture. We will also understand how does a MapReduce job execution work. We'll understand terms like rack awareness. We'll also understand how does a file read and write happen in Hadoop. And then we'll also take a sneak peek on the Hadoop 2.0 architecture. Okay. Now let's look at what is Hadoop. Okay. Now Hadoop is not just a distributed file system. Hadoop is a framework that allows for distributed processing of large data sets, as we've just seen, across clusters of commodity computers using a simple programming model. Now, though I'm not a big fan of definitions, but this one is a good definition. So Hadoop is a framework. Now there was a question that there are many other distributed file systems available. Google has one, the Red Hat ones has one. Hadoop also has a distributed file system. So Hadoop is not just that distributed file system. It is a complete framework which allows you to do processing over large data sets across clusters of commodity computers using a simple programming model. And this simple programming model is called MapReduce. And we will be looking at that as well as we go ahead. So in Hadoop, you can scale up to any number of nodes in a cluster, which means that what Hadoop does is that it gives you the power to distribute your data across a cluster of commodity computers, and these could be as big as 10,000 nodes, okay, where your data is stored and it can be retrieved in parallel. It can be, a lot of parallel processing can be done, distributed processing can be done using a programming model called MapReduce. Okay, and we will be going into details of each of these things as we go ahead. Okay. And it is an open source data management with scale out storage and distributed processing. So it's an open source data management tool. Now the key features of Hadoop, we will also come to know about them as we go ahead in the course, but for now it is economical. Economical, why? Because one, there's no license cost associated with it. Even if you're buying a Hadoop from Cloudera or a Hortonworks or say MapR, which are different distributions of Hadoop, you still have to pay only for support. The distribution is free of cost. Okay, so it's more like Red Hat Linux and not like Microsoft Windows. Okay, so it's economical there. Reliable, the system has been built in such a way that when there are failures, you still have data availability. Okay, and we will be looking at that. There's something called data replication, node replication. I'll be teaching you that. I'll be talking about that today in the class itself, so that you come to know that how does the system remain reliable as well. Okay. Flexible in the sense that you are not constrained by the number of nodes. You can keep on adding nodes on runtime. How do you add nodes? What is the effect of adding nodes on the admin module is something we'll come to know. But for now, you can understand that you can really delete and add nodes without putting the system down. Okay. Scalable, it is largely scalable. There's no limit on the number of there's no limit on the number of nodes you can add, and basically your solutions like Teradata and Exadata cannot work for if the data becomes large than say 10 terabyte. Okay, so that is where Hadoop comes into play. Hadoop can process really large data sets, maybe in the order of petabytes as well. Okay, and there is no limit to the scale as such. I mean, theoretically, there is no limit to the scale. Okay. Okay. Now coming to the Hadoop ecosystem, let's see what are the different components in Hadoop. Now I'll not be going into details of these, but over the period of our course, we will be covering most of these. Okay. Okay. To start here, so basically you had a lot of data or a structured data. If you had structured data stored in a RDBMS and you want to move it into Hadoop, you use Scoop for that. Scoop is the tool used for Scoop is a tool which is used for moving the data from RDBMS to Hadoop. So it's a full form of SQL to Hadoop. Okay, it's the abbreviation of SQL to Hadoop. Okay, so this is where we'll be using Scoop. We'll be covering Scoop in the course in the class 2 itself. We'll be talking about data loading techniques. Flume is used to import unstructured or semi-structured data into Hadoop. Okay, which means that say if you have data which is on web, okay, and you want to move that data using an API into Hadoop. Say a common data could be a Twitter data which you want to move into Hadoop. Some websites will allow you to import data directly from an API. So Flume is the tool used to do that. Okay, we'll be doing an example of Flume also in the next class, and where we'll be loading data from Twitter into the HDFS or the Hadoop distributed files. Okay. At this point of time, just try to understand, just get familiar with these names. Okay, Hive is the data warehousing system in Hadoop. We'll be covering that as well in one of the classes going forward. This Hive was developed by Facebook. Pig is another data analysis tool in Hadoop framework which was developed by Yahoo. We'll be covering that as well. Now, then Mahout is the machine learning framework. It is used for doing all those analysis like recommender systems, clustering analysis. All those things are used in Mahout. It is the machine learning component. Now, a lot of applications use machine learning as well these days, especially the e-commerce and your social media. They use a lot of machine learning. In fact, Mahout is being commonly used in almost all the domains these days. So this could be another thing which will be interesting, but we will not be covering in this course. It is not a part of this course. The Oozie will be covering in this course. This is the workflow management tool which is used to run jobs in parallel on Hadoop. Okay. MapReduce. Hadoop, Scoop and Flume are tools. Okay. Scoop and Flume are tools, and don't worry about them too much right now. Okay, you need to just know the names right now. Okay, going forward in the next class, you will understand how to use Scoop and Flume also. Okay, for now, just get familiar with these names that is used to move data into HDFS. Okay. Now, Mahout will not be a part of this course, so I'll just quickly tell you a little bit about Mahout. There's a separate course on Mahout, so if anyone is interested, you can pick up that course as well. Okay, so Mahout is basically Hadoop and MapReduce together. You can write intelligent applications using Apache Mahout. You can also look at this link, which will tell you a lot of things with a lot of people who use Mahout. And these are the, I'm sure everyone has seen these kind of recommendations on LinkedIn. Companies you may want to follow, jobs you may be interested in. People who saw this profile also looked at. Okay, people similar to this, I'm sure everyone has seen, right? Or the recommendation which you see on Amazon, all that is done using Mahout. Okay, Mahout in itself is a big subject, but yeah, it is a part of the Hadoop framework. So you may, if you're interested, you may want to learn that. There is a course from Edureka, I believe, which takes you deep into Mahout as well. Okay, but we will not be covering in this course. Okay. So is this clear to everyone? What are the different components in the Hadoop framework? In the Hadoop ecosystem, you have the tools for loading data, which is Hadoop distributed file system, and then you also have a NoSQL database in which you can load data, which is HBase. MapReduce framework is the programming model which is used to read and write data from this from the distributed file system. We'll go into details of all these are open source. Okay, all these are freeware, all these are open source, right? Okay, then Hive is the data warehousing tool, Pig is the data analysis tool, Mahout is machine learning, Apache Oozie is the workflow management tool. We'll be looking at each of these tools and their applications as we go forward. Yes, MapReduce framework works directly on the HDFS, and I'll also tell you what is MapReduce in a while. Okay, I'll give you a small example of MapReduce as well. Okay. Now you can, okay, good question, which reporting tool is used? Okay, so for data visualization, a lot of people use R there. R is an open source reporting tool. Has anyone heard about R? R is a library of, you can do trend analysis, you can do predictive analysis, you can do a lot of things using R. Okay, so R is an open source tool which is used in conjunction with the, it is a language in itself. It is very similar to SAS. As such, SAS is basically very high cost license. There is open source. A lot of people are, yes, it is called R only. R, the letter R itself. You can search for R programming language. It is used in all the domains. It is used in financial domain as well, and there is a course on R as well in Edureka. You may want to look at those details as well. So it is used for, yes, so you can use it for risk analysis, you can use for predictive analysis. With all this data which you have in the Hadoop ecosystem, you can use R to generate meaningful analysis out of that. Okay. Nirupam says, I've worked with R, it's a powerful statistical analysis tool, right? Okay, so let's move ahead. Let's look at the core components of Hadoop. So Hadoop has two core components of Hadoop. There are two core components of Hadoop. Okay, one is your HDFS, which is the Hadoop distributed file system. The other one is your MapReduce, which is used for processing. Now, as we've seen, Hadoop distributed file system is nothing but a set of clusters or a cluster of machines which are combined together where the data is stored. Okay. Now there is in this there are two things here. One is called a name node. The other one is called a data node. Name node is used to do is the admin node there. Okay, and the name node is called the admin node, and the data node is your regular data node where the data is stored. Okay, so we will talk about more detail into name node and data node. For now, you can understand a cluster or a Hadoop distributed file system consists of two types of nodes. There is one name node and there are multiple data nodes. Data nodes is the actual node where the storage happens. Okay, and if you look at that powered by link which I pointed you earlier, you will see the kind of cluster people have built, the kind of data, what is the configuration of that machine which can be used for data nodes, the configuration of machine which can be used for name nodes. Okay, now the data is put across data nodes. Okay, now they are natively redundant, which means that the redundancy is built in. The redundancy is built in the sense that all the data which is present on one node is replicated on other nodes as well to avoid failures. Now, since we use commodity hardware here, we assume that the data is going to be that the data node is going to fail. Okay, so with that assumption in mind, the way the framework works is that it doesn't store data at a single location. It stores the data at multiple locations. And how is all that managed is something we'll be learning in a while. Okay, in today's class going forward, we'll be learning that. Okay, for now you can understand that HDFS is a Hadoop distributed file system. The data will be stored at multiple places, but what will happen is that this data will be stored at multiple locations, but it will be governed by a single admin node which is called name node, but you can read the data in parallel from multiple nodes. Okay. MapReduce is a programming model. What MapReduce does is that to analyze your data, okay, you can run your program instead of moving your program into. Okay, let me take an example before I make you understand what is MapReduce. Let me just quickly put a blank slide here. I'll give you an example now. Since this is a election season in India, let me take an election example itself to make you understand how. Okay, just bear with me with my bad handwriting, but let's take a pen and okay. So basically, assume you have elections happening in multiple locations. Okay, so these are all multiple booths. Let's take an example of a election campaign. Okay, these are all multiple booths. Is everyone able to see this? Yes, yes, Ananda. HDFS has complete file system structure. We will be looking at that as well. We'll go into the details there. Just hold on for some time. Let's try to understand how does MapReduce work. Now these are multiple locations where people you went and voted. Okay, people in Delhi, Chhattisgarh, in India especially the elections are going on, and the similar is the case everywhere wherever elections happen. There are multiple booths where people go and vote. Okay, so say I went and voted here. My vote is registered in this location. My friend's vote is registered in this location. Okay, There are multiple parties which are contesting these elections. Okay. Now one way of calculating who won is to take all these votes from here and move them across to a central location. Okay. And do the counting at this location. Okay. And declare a winner. Okay, so this is one way of doing things, right? And this is how traditional systems work, right? Everyone agrees with that? Does everyone agree? Can I get a yes? So you have so many people who have voted here. There's so many people who have voted at this booth. Take all these votes. Now assume that you did not have EVMs, you had votes. So you will carry them across and you will do the counting at a central location. Okay, right? What are the challenges here? Now these could be lakhs of booths across the country if it is a general election. The challenge is moving this data across from this place to this place. The cost of moving data is much more than the cost of doing the calculation. Right? Processing cost is lesser than the cost of moving data. Does everyone agree with that? Moving data is difficult and time taking. That's right. Very good, Maruti. Right. So what could be the alternate solution? Let me try to see if I can get rid of this animation. Okay. The alternate solution could be that on these booths, you send your processing to these booths. Okay. So I voted here. You calculated at this point itself that party A got these many votes. Okay. Party B got these many votes. Similarly at all these locations. Okay. Count at the booth itself. Very good. So then, but can you declare a winner at this place? Yes, you cannot declare a winner at this place because it will be dependent upon all these locations, and together you will be able to tell whether if the party wins here, it doesn't mean the party A will win at every place, right? You need to consolidate. So what you will take from here is the data you will take from here, and you will move this data to a central location where you will consolidate this and do a processing here as well and declare a winner. Right? Does everyone agree with this approach? This looks like a better approach, right? Okay. So this is what MapReduce is. Okay. A is a party, nothing more, Prakash. A is a party, A and B are two parties. So let me talk once again about this. So initial method was that you have all the booths, you take all the votes and move them to a central location and do the processing there, right? That was the traditional approach we looked at just a while back. In that approach, the challenge was that moving data, the cost of moving data is very, very high, okay? And the cost of, and the time it takes is very high, so your processing becomes time taking, tedious, and very difficult to do. Okay. While in approach 2, what we did was we counted the votes here itself and only moved the part that how many votes did each person give. We did not move the votes literally from this place to this place, right? Data loss chances are also very low. That's right, across the network. So, so this task of counting here is called a map task, and this task of finally doing a deduction is called a reduce task. Okay, these are all programs. Now initially what the approach was to move your data to your processing. Here what we have done is we moved the processing to the data, right? Is that clear to everyone? Yes, you can do That's right, Ipsha. You can do, and all these maps can be run in parallel at multiple nodes. That is very easy to understand, right? You don't need, so there can be booth level resources who can do this counting. There can be booth level resources who can do this counting and only pass on this particular thing, right? So this is the map reduce approach of solving a problem. Okay. The reduce task is again a program which will just consolidate. Okay, if a party got these many votes from here, it will get the tally of all the votes from all these places and then finally tell you who is the winner. Is that okay, Richa? Yes, we are still moving the summaries of individual nodes to central location to consolidate, and that is what the reduce task will be doing. Okay. Sure, I will repeat this once again. Richa, Jatinder says, excellent example. Thanks, Jatinder. Sure. So the summary of this whole idea is, I'm sure when you read about MapReduce, you will be hearing terms like moving data, moving processing to the data, moving the program to the data. This is what it actually means, that you divide the whole problem into multiple problems and solve those problems. Now, what we've done here is, since this data was available here, instead of moving the data to a central processing unit, we moved our program to this unit. So basically you can move a map task or a map program to the data node where the data is actually stored. If you come to that, okay, and you get a consolidated winner at this booth level. Then you take this winners or from all these booths to a central location. This could again be a data node. I mean, it doesn't matter. This could be another constituency where you took all these and you did a calculation here on who is the actual winner, right? Is that clear, guys? A map is just a program. We'll come to know about that as well. Okay. It is called map reduce because the first task is called map task. The second task is called reduce task. Okay. Is this clear to everyone? That's right, Venkat Subramaniam. Anyone has any doubt about the map reduce paradigm now? Don't worry how the map task is run, how many map tasks can be run on a node, who governs, who makes sure that the task is running properly. Okay, so Anup says, sorry, the example is not clearly mapped to map reduce. Anup, why do you say so? What is missing here? What did you not understand here? Okay, so on the individual poll booths, a map task can do the calculation here itself, right? The task can be completely independent. There's no dependency of this task on this booth, right? Say on booth A, you have a party candidate A which is leading and you get these votes counted. You get 50 votes here, you get 45 votes here. Now you move not the votes but the actual number, that 50 and 45, to this task. So this is any task which can be done independent of the other data nodes can be moved into a map task. Okay. Wherever there is an aggregation required, you require a reduced job. So it is also possible that in your analysis you never have a reduced job. You can do everything in a map task itself. Say for example, if you are doing an encryption on some data, okay. We will not get into those details, Venkat, right now. What will happen if the one map task fails? We'll get into that going forward. But for now, you just try to understand this. Let's take an example of something like you have a lot of data, raw data kept in multiple nodes in Hadoop, and you want to apply an encryption algorithm on that data. Okay. If you want to apply an encryption algorithm, it will just be a transformation. You take X amount of data, transform it using an algorithm, right? Using a function, right? That function does not require consolidation across nodes. So you can run a map reduce without a reducer itself. Does that make sense, guys? Does that make sense, what I just said? That's right, Prem. That's right, Anup. That's right. Okay. Okay, so I'll explain this example once again. It's a little difficult thing to get at this point of time, but don't worry, I just want to have some chaos in your mind as well. So what I said was that you have huge amount of data put across multiple nodes in a cluster, okay, and you want to run an encryption on that. You want to encrypt all that, okay. So you can run that. And what does the encryption require? It requires a data transformation. You can use a function which will just take the input data and give you an output which will be encrypted data. Is that clear to everyone? So you have a function A, okay, which will take an input I and it will give a output O, okay, right? And this is the, say for example, AES encryption, and AES is the type of encryption, right? You can, if you have say 100 terabytes of data here, you can run this function on this whole data, and this, what will come out of this will be a encrypted data, right? So in this case, you can do all the tasks, whatever is required here in a map task itself. You don't need a reduced task in this job, right? Because you don't need any consolidation. Is that clear now? So there's something called a job tracker, then there's something called a task tracker. Now on the MapReduce engine, there's something called a job tracker and a task tracker, okay. On HDFS, there's something called a name node and a data node, okay. So the way it is divided is that HDFS will have a name node which will be the master node, and then there will be data nodes which will be slave nodes. Job tracker is the master daemon which runs and distributes the tasks to the task trackers. Which task trackers are the programs which will be running on the data nodes, okay. Okay, so basically for now just understand that there's something called a job tracker and there's something called a task tracker. Job tracker is associated with the master node, the task tracker is associated with the data node, okay. For now that's all, right? Task trackers data nodes are the polling stations. Task tracker could be the program which is running on the for counting the votes at the polling station, okay. Okay, the tracker runs on the data node. Data node will be on a machine and the tracker will be running on that node, okay. So job tracker is associated with the admin node and the task tracker is associated with the data node, okay. Is that clear to everyone? Just remember this much. No, wait. Don't get into map task for now. Okay. Yes, task tracker will be controlling the map tasks. Okay. But for now, it will be controlling the map task, but it is not the map task. Okay. It is like it is a service which is running, something like a Windows service or a Unix daemon. Okay. Okay, so just remember these terms that we've now understood what is map, what is reduce, we've understood SDFS, we've understood what a cluster means, we've also understood what is a name node, we've also understood what is a data node. These terms just become familiar with these terms. A map task is nothing but the map program of the, okay, a reduced program and a map program. Okay, Ananda, that question will be answered in a while if the name node is a single point of failover. Technically speaking, these are daemon threads. That's right. Okay, let's move ahead. Let's look at the architecture of the HDFS. Okay, now this is a very important slide. So just make sure that you are paying attention to this and try to understand it once. I'll repeat it also, so don't worry if you do not get it in the first chance. So the end user is talking to a client. Okay, end user will always be interacting with a client. So a client could be, say, an interface built over Hadoop, which you can, we will be looking at a few clients going forward. So it could be the command line interface where you can run commands on HDFS. Okay, it could be a Java-based interface on which you are using which you are interacting with the Hadoop cluster. So that's what the client is. Okay, and the end user will be sitting in front of the client. Okay. Now, the client will be interacting with the name node with respect to the metadata operations. So all the metadata operations will be done through client. Okay, so what does that mean? That means that if I have to find out what all data nodes are free, where can I write, or from where can I read a particular block, I'll be talking to the name node. Okay, name node will give me that information, and then I'll go ahead and read that data from the either the data node or write that data into that. So this client and this client are same. This is just for representation purpose that we put it here. Okay, fine. So, and I'll be also going into the details of how a read and write happens. For now, you can understand from this architecture that there's a name node. There will be multiple racks on which the data nodes will be there. There will be multiple blocks on which, on a particular data node, the data will be divided into multiple blocks. Okay, and there will be a specific block size of this data. Okay, and if you have to read or write a data, you will first talk to the name node, find out the availability of that data if you want to read it, or find out the availability of space if you want to write it, and then name node will tell you, okay, this is where you can go ahead and read it, or this is where you can go ahead and write it. Then the client will go ahead and read or write from that particular location. So let's move ahead from here. Yes, these are auto triggered. Okay, some of these things will become clear, guys. Just hold on for some more time. Let's look at the name node and a data node, and a lot of questions about failover and all will be answered here. So name node, as you can see here, is, can you identify this car, guys? Everyone can identify this? Okay, a lot of people have been able to identify it is a Lamborghini. Okay, now a name node is like a Lamborghini. It is the master of the system. It maintains and manages the blocks which are present in the data node. Now this is a very high availability machine. This will be a this will be a machine which you will probably, it will cost you a lot of money. But the whole idea is that in Hadoop, this is a single point of failure. Now, just to be very correct, in Hadoop 1.0, it is a single point of failure. I'll talk about 2.0 as well, as I promised you in the beginning, but let's assume that since it's a single point of failure, this is a very expensive, high availability machine with multiple processors working in parallel there. Okay, and it is a single machine in a complete cluster. There is no multiple name nodes, there's just one name node in a machine. Okay. Okay, so typically this could be a RAID machine as well, and if you want to know about the exact architecture, exact configuration of this, I'll send it to you in a note separately, Ashutosh. And for everyone else as well, we'll have something there, right? The typical configuration of a name node and a data node, I'll share that with you. Okay. Now, this will have, say, multiple power sources. You will do everything which you would probably do in a Lamborghini to make sure that it doesn't fail. Okay, whatever, there's no replica for name node. Just hold on. There is something, but not really. For now, you can understand, and very shortly you'll understand what are the other things associated with it. So it will be a very high quality, high availability machine with multiple power center sources. It will be kept in a place where it should not fail. It will not. Okay, there will be multiple processors running. There will be a huge amount of RAM associated with it. Okay, so all that is happening here. All the data which is stored is never stored in a disk. Here, all the data will be available in the RAM itself in the name node. Okay, so the best-in-class machine which you can get, you will use for name node. The exact configuration, I can share that with you. Okay. Now, what is a data node? Now, as we said, right, commodity hardware, and you can look at this analogy. These will be like these ambassador taxis, which could be, you don't worry about the reliability. You can just, these will be huge, cheap machines which can be commodity hardware. Okay. Okay, so Venkat says the data nodes ambassadors are much stronger than the name node. Okay, the Lamborghini. Well, I mean, yeah, they are much powerful because all the politicians go in them, but they are still commodity. Okay, so like, let me not get into politics right now, but at the same time, what I wanted to tell you here is that data nodes are plain commodity hardware, but commodity hardware is a normal machine. Your laptop can also work as a data node in a Hadoop cluster. As simple as that. No special thing about them. Okay. And they are bound to fail. Okay. They are assumed to be failing. We don't maintain a high quality machine here. So that's where the cost of the overall Hadoop cluster is very economical. You can use commodity hardware here.